Well, delighted to see everyone for this, my final Gresham lecture. It's, well, you're not supposed to... I don't think you're supposed to cheer when I say it's my last. Oh, that's better, yeah. So I've decided my swan song's going to be looking to the future, looking at some of the issues which I've not had time to touch on, and much more of a sort of umbrella talk about where astrophysics and cosmology may be going in the future. And by the future, it could be within the next few months. It could also be in the next few decades. Lord Kelvin, that great scientist, is supposed to have said, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." Now, unfortunately, he said this in 1900, a couple of decades really before you have the worlds of general relativity and quantum mechanics revolutionising physics. So it was kind of unfortunate timing. Today, I'd say astronomers are a bit more cautious. We're all too aware that over, just the last couple of decades, we've discovered, 3/4 of the universe we didn't realise was out there. We've discovered, 2,000 planets around other stars. We're well aware that there's plenty more to discover, or to sort of quote Donald Rumsfeld, there are plenty of unknowns out there. And in fact, we relish that. We bank on there being things to discover. If there wasn't, I think we'd all feel a bit cheated. So there are plenty of exciting things left to find out. Now, the great thing about astronomy is a multidisciplinary science. You're bringing together maths and physics, chemistry, geology, even today biology, to tackle some of the most fundamental questions that there are. And the other great thing about astronomy is it's the science of extremes. And we're talking extremes of properties such as density and temperature and pressure, but also time and distance and mass, all these scales together. And it means you can test the laws of physics under these extreme conditions, and in conditions that you can't possibly reproduce in the lab here on Earth. This gives it the most exciting potential to basically attack the most fundamental questions, I think, that there can be in any of the physical sciences. And this is what makes astronomy so attractive, not just to young students coming through, scientists researching it, as their careers, but also to the layperson and the general public. Now, in the last 4 years of lectures, I've covered some of the most obvious topics where either there's observations, they're in dire need of theory to back them up, or even cases where there is theory, where they're in dire need of observations to map the predictions that they're making. And all of these are very active areas of research. So, for example, we have explicitly covered the whole area of dark matter. This mass that's out there, it's got gravity, but it doesn't interact with light in any way. And yet there's 5 times more of it than the ordinary matter that we observe with our telescopes. This is an area where maybe with the advent of the new high-energy collisions that are going to be going on the revamped Large Hadron Collider, maybe we're going to start discovering existence for those massive particles that are proving so elusive that only weakly interact with ordinary matter. It could be that there's going to be other direct or indirect evidence. You've got the LHC coming online. There are also experiments going on, such as the Lux detector that I talked about in my previous lecture a couple of months ago. It's possible that we could learn the answer to dark matter within the next couple of years. Certainly the signs are very hopeful. When it comes to the other 70% of the universe, is a little bit more elusive. This is the dark energy. This is the repulsive force that's creating the accelerated expansion of the universe that was discovered back in the 90s. It has very important implications for our whole understanding of physics, but actually pinning down what it is going to be a little bit more difficult. Again, the Large Hadron Collider, the collisions going on there may elucidate the nature of the dark energy, but perhaps we're going to have to wait a little bit longer. There are missions such as WFIRST, which is a NASA telescope. That's going to be going up in the 2020s. There's a European Space Agency mission called Euclid, which is going up sooner in 2020. These are going to be looking at the distribution of mass on the larger scales. And it's looking for what we call, if you want a good buzzword, baryon-acoustic oscillations. But basically the distribution of matter on the greater scales. And that is something that you can then tie to predictions from different types of dark energy. So the time frame for solving that is slightly longer, but it's still within perhaps the next couple of decades, the next decade, that we should begin to see big changes in finding out about dark energy. But there's plenty of other things out there that we are still struggling to understand, that I've talked about in my lectures. You have those very transient phenomena, the most explosive events in the universe, such as gamma ray bursts and fast radio transients, things that we see going on. You have this fantastic burst of energy released, in it, working out that energy release, what it comes from, how it's powered, is proving, again, still very difficult to follow up with observations, though we have plenty of theories. I've also talked about the early universe. We propose that this whole generation of the very first stars, how they affect the gas and the universe around them, how they might eventually go on and form the very first galaxies, and how these build up. But this is still a region that is, we think about this, we have theories, it is totally inaccessible currently to observations. Again, we expect big changes to happen, big advances to occur, but we're going to have to be patient. Probably the way to crack those will be when the next generation space telescope, the James Webb Space Telescope, is launched in 2018. That's going to work exclusively in the infrared. It's going to be very sensitive to things that are very faint and very redshifted, and perhaps open up that window to where the first galaxies are beginning to form. Even, well, slightly closer to home, we have problems again where we see something. So, for example, massive black holes, supermassive black holes in the cores of galaxies. From the observations, we see them launch fantastic thin collimated jets of material that squirt right out of the galaxy into the space beyond. Artist's impression, by the way. If we had observations this good, we wouldn't be speculating quite so much. But we see these jets originate out along the rotational axes of the black hole. And we have ideas, but it's still very vague as to how you actually launch these spectacular streams of relativistic particles from so close to the black hole, and you sustain them over such lengths of space. And going from physical processes around black holes, again, we've also had revolutionary advances in discovering planets around other stars. And again, this is bringing up even more questions than we ever thought we had in the first place. We're discovering that many solar systems look nothing like our own. How special is our solar system? How special is our Earth? What are the conditions that give rise to this multiplicity of different planetary systems? So there are no shortage of big questions. And big questions are important because they are what motivates an interest in the first place, that gets many of us galvanised into studying astronomy. But having fundamental questions that you have the possibility of solving it may be a great motivator, but it's not very practical. The real challenge for the modern scientist is whittling down those big questions into the right questions, the ones that you maybe have a chance of solving and advancing, maybe not answering the fundamental question, but advancing our knowledge towards that answer, even if it doesn't happen in our lifetimes. Astronomy is very much a data-driven science. Again, I admittedly am an observer, so I have a slightly biased viewpoint in this regard, but I think a lot of the step changes come when there are new advances in our detection. The most obvious one here is when Galileo first used a telescope for astronomical observations. Now, his observations of, the sun's rotation, the phases of Venus, the moons around Jupiter, the mountains and the craters and the structures on the moon, these were the first proof that revolutionized some of the theories about the structure of our solar system. And so it's when these new facilities come available, new observations are made, that the theory follows, and they challenge the theory to match up to it, or they challenge the predictions from the theory. Right from the first telescope, that's still true today. This is one of the reasons why astronomers are always pushing for the next big telescope or the next big space telescope. Bigger, better telescopes, whether it's the 8 and 10 metre class telescopes that we have in ground-based astronomy today, with their detectors and their instruments, and looking ever ahead to where we have going to have telescopes that have got 39-metre mirrors across. We're always pushing for those new facilities because they're the things that are going to change our view. We're going to detect new things. And it's not just the size of the telescope and its power, it's the nature of the detector you put on it, and it's also the ways you have of sifting through the data to pluck out the relevant information.
All of this is as important as just pointing your telescope in the right place at the right time. The new facilities drive the data that we get. And it's not just the new facilities. Obviously, if you get a new telescope, it enables you to see new things. Never is this more true than when you open up new windows of observation in different wave bands. For many years, we were restricted to visible astronomy, using just the usual optical part of the wave band. In the 1940s, radio astronomy opened up, and we discovered completely new things about the galaxies that we'd hitherto thought were just, stars and gas. In the 1980s, you start getting infrared astronomy, where we start to see the very cool regions of the universe. During the 1960s and 70s, we get X-ray astronomy, where we see the most explosive, the hottest, the most energetic regions of the universe. And every time you open up one of these new wave bands for the observations, you discover a whole tranche of places that you didn't realise were exciting and phenomena that you didn't realise were so exciting within the universe. Now, we've effectively opened up the full range of the electromagnetic spectrum. There are no new windows left to discover, though, of course, we can go deeper and we can discover new objects or new facets about the objects that we've discovered within those windows. But we're not likely to be discovering new processes as such. So having explored the full range of light out there, the next big step, as I talked about, again, just a few lectures ago with the transient universe, is about time domain astronomy. This is where watching not just the light that things give out, but how this changes from one day, 1 week, 1 year to the next. And this is where there are going to be the big advances. Right now, the ESA Gaia satellite is more or less taking a 5-year movie of the sky, looking for those changes that maybe indicate a supernova going off or a nova or stars at the end of their lives or things flickering or bursting, changes in quasars very far away, looking for those minute changes that happen that normally we would miss. The next big step would be the LSST. Again, huge new advance coming online within the next decade where you're scanning the sky every few days, looking for changes that are happening. These are the things that are going to revolutionise our view of astronomy in terms of the data collection. It means that you don't just happen to be lucky to be looking at the right place at the right time to see something exciting happen. Of course, it's not enough to be the first one with a telescope, be the first one with a new space mission that's looking in a new window, to actually realise that you're seeing something new. There is more to it than that. For example, I talked about Galileo with his telescope. Here, if you compare Galileo's drawing of the surface of the moon with his telescope and a drawing done by Thomas Harriot, who in fact used the telescope earlier than Galileo for observations of the moon and other objects in the sky. You see that they both see the same things. The difference is that Galileo uses what he sees to speculate and to ask further questions and to make inferences. Observations aren't enough. You need to have the right kind of mind to interpret them. Serendipity plays a major role. You've got to have the luck of being the person to see that observation or to detect that particular galaxy as it's an outburst or to see something going on. But serendipity, that luck, is not everything. You need to have what's known as the prepared mind. Now, this comes from the quote from Pasteur, who is supposed to have said, "Chance favours the prepared mind." And this is the idea that you need to recognise a major discovery when you have one. You need to know what's normal, what's boring, to be able to recognise when you have got something that's new that is potentially going to change the whole paradigm of the subject. And there are many examples of fantastic serendipitous discoveries throughout astronomy. You can go right back to 1800, where Herschel discovers the infrared wave band, that the fact that there are other lights, other colours beyond the visible spectrum, again, just by chance when he's doing an experiment to measure the temperatures of different colours. The discovery of X-rays 95 years later by Röntgen is again a serendipitous occurrence. These then have the implications that, within the centuries, you then get new areas of astronomy and you see those new facets of cosmic objects. But it's not just these wave bands were serendipitously discovered in the first place. If you think of the very first exoplanets that were found, they were discovered in orbit around a pulsar, a dead star, one that's gone supernova and thrown off its outer layers. It's the last place anybody would ever have looked for a planetary system. But the presence of these planets was detected by variations in the pulse, just showing how the gravity of the planets changes the spin of the pulsar. This is a discovery that nobody had anticipated, but in 1992 was the first clear evidence of other planets out there where nobody was coherently looking for them. And indeed, when you first find proper exoplanets, well, not proper, these are still proper, but find exoplanets around a normal star, again, it's not just enough to detect the signal. You have to do this shift in your thinking. That the breakthrough could have been made earlier. The difference is making that detection and changing your whole view of what it is you're looking for, realising that maybe you've got to change your view of what planets are out there. Again, this is an artist's impression of a hot Jupiter, but the idea that you could have other systems out there that don't resemble anything in our own solar system. You could have giant planets several times the size of Jupiter in close orbit around their host star. Things that people were not originally looking for. You have to recognise that as serendipitous discovery and then work on the interpretation to realise what it is you've discovered. There are other examples. Again, the discovery of pulsars in the first place in 1967 relied on finding a radio signal that was substantially different from other radio signals out there. There are tales that actually the pulse signal in the radio had been detected before from military-based installations in Alaska. The difference is actually the curiosity to follow up that pulse, to search down what could be the origin for it, and then make the big discovery. And of course, the most revolutionary one of recent times, Perlmutter, Schmidt, Rees and their collaborators were looking for the point where the expansion of the universe started to slow down as a way of measuring the mass of the whole universe. At what point does gravity kick in and start slowing down this expansion to bring everything back? And they didn't discover that. What they discovered was unanticipated. The fact this expansion is not slowing down, it is accelerating, it's getting faster. And from that observation, which is again serendipitous, they discovered this 3/4 of the universe, this dark energy, that we were unaware was out there. So here again, serendipity plays a major role, but not just serendipity, it's a recognition, an ability to interpret what it is you've discovered. So despite me standing here and saying, well, obviously it's data-driven, it's the observations that lead the science, there are parts of the universe which are not accessible to observations. There are regions that will remain hidden from us for the tangible future. And there are regions that are not just hidden from us in observation, but also in theory, because we don't have a coherent framework to explore them. And these regions occur in astronomy where you have a lot of mass compressed down to a tiny volume. So here we're talking about extreme states of matter. We're talking about those extremes I was talking about before, extremes of temperature, of mass, of size. Temperature and density billions of times greater than we could ever measure in the lab here on Earth. So, for example, whatever the early version of the universe is, just those first milliseconds after the Big Bang, what lies perhaps within right at the core of the black holes. And the reason this is inaccessible to us, even with theory, is that we don't yet have the explanation in physics or the framework in physics to deal with them. Astronomy has been fairly unique from the rest of physics in that it's driven by gravity. The framework we use for astronomy is one of general relativity that describes everything that's going on in the cosmos with great detail. The rest of physics, happily, is described by quantum physics. But here you have the point with the early universe or the core of a black hole. You have got So you have really powerful gravitational forces acting over quantum distances, subatomic scales, over tiny distances. And this is the difficulty where you need to try and reconcile gravitational forces with the quantum world. And at the minute, we can't unify the quantum with the relativistic world in one coherent framework. There are theoretical ideas that seek to unify the two. This is the idea of unification I've talked about in the past. It's a stumbling block for us at the minute, but it is also exciting. It may be a problem for us at the minute, but it also means that astronomy and certain regions of astronomy hold some of the biggest challenges to this framework, and it's quite possible that the advances in dark matter and understanding dark energy will ultimately lead us to this idea of how we unify all the four forces within one set of rules of physics. There are, of course, ideas, things such as supersymmetry, ideas such as M theory. You may have read about these, heard these words bandied around. Some of them also cause problems. For example, M theory prescribes that there are extra dimensions rather than the three we need to pin something in space and the time to pin the occurrence of that thing in the history of space. They also require perhaps that there are other dimensions. So, for example, M theory suggests there are extra dimensions in space, and these sort of 6 or 7 extra dimensions are coiled up tightly within subatomic timescales. Talk about inaccessible regions of the universe. How do we ever tell that they're there? Well, there are possibilities if these theories are right. Maybe gravity is the weakest force of the four because it's the one force that leaks out into these extra dimensions. And so you have the possibility of testing unification theories if we could ever test gravity on these minute scales. You know, does the gravitational inverse square law break down on sort of millimetre or less scales? These, again, just show you some of the possibilities, some of the questions that people are actively grappling with. And of course, once you start getting this idea of unification, we have a framework that maybe allows us to deal with, powerful gravitational forces on a quantum scale. Then we can start asking or answering those really fundamental questions like what triggered the Big Bang? There are ideas, say, if you talk about M theory, you have two multidimensional universes colliding, causing some outburst in a subset of those dimensions. You can go and read all these wonderful books that explore these ideas, but they are still quite speculative. These are still regions that are hidden from us from theory and from observations. The very first observations we can make are of the cosmic microwave background. This is the light that was released when the universe stopped being opaque, became transparent, matter collapsed for the first time into atoms, stopped interfering with photons, they could stream across space towards us. This is the earliest light we can actually observe. But at this stage, the universe is already 380,000 years old. An awful lot has happened that we can't see. And one of the things that we're very excited about, again, there's this fantastic theory called inflation. We need inflation to have occurred between the Big Bang and long before the cosmic microwave background you see here. Here's just a schematic that I quite like, where you start off with the Big Bang at the centre and time unfolds in a non-linear manner counterclockwise here. And you go from this, when the universe was quantum size, we call this the Planck era, and when the universe was probably about 10 to the minus 34 seconds old, it then starts doubling in size. This is the period of inflation, when you grow it from something that's quantum sized to something that's maybe the size of a melon, and it doubles in size it doubles in size every tiny fraction of a second, and then suddenly that period of inflation stops. We need this to account for the fact the universe looks the same in all these different directions, that the curvature in the space of the universe is almost flat. We need this inflation to have happened. Seeking evidence for it, again, it's a theory that we want to be true. Seeking observational evidence of it is very difficult. You may realise there was a great excitement just about 18 months ago, probably a couple of years ago now, where there were ideas that perhaps in the polarization or some of this cosmic microwave background light is polarized, and there was a twisted signature in it. This was done with an experiment called BICEP 2, which is down at the South Pole. It looks like a nice Bond layer there, I think. And it's had this, they've just looked at a small part of the cosmic microwave background light, and they saw this twisted pattern within the polarized light, which they interpreted as ripples that are due to, well, I'll talk about gravitational waves later, but basically the material space being set in motion by this period of very rapid inflation. This was touted as evidence for inflation. Unfortunately, the signal is there, but as been found since by the European Planck collaboration, where they look at the whole sky in more detail, there is that twisty polarization signal across the sky, as this image is trying to show, but a lot of it is due to foreground dust lining along the tangled magnetic fields in our galaxy. And so the observational proof of inflation has receded. It doesn't mean that inflation is wrong. It just means we don't yet have the observational signature that we require. And again, this will be something that we've got to go back to the drawing board. We've still got to go and find proof of that huge burst of inflation, and we haven't yet got the proof. So not only do you have inflation, but after that, you still have something else that is causing a great conundrum. We think inflation happened, we still have to find proof of it. But there's another big problem that we don't understand. One of the big questions is about the nature of stuff in the universe. There's a point when the universe is perhaps a trillionth of a second old, the temperature's 10 trillion degrees. It's so full of energy, it's completely energy rather than the matter. And you have pairs of particles and antiparticles are created. Oops, I don't know what that is. Let's go back. Pure energy creates pairs of particles and antiparticles. And what these are, if you have a particle, for every particle there is an antiparticle that is a mirror image of the normal stuff. It's the same in every way, except the electric charges are reversed. So for an electron, you have a positive proton. For a proton, you have a negative antiproton. Neutrino, the spin goes the different ways. For every atom of hydrogen, you'll have an atom of antihydrogen. So the idea that all of this is created in the early universe, when it's so hot, so energetic, after that, the universe expands and it cools down. You no longer have enough energy to create these pairs, this matter. The problem is that we expect that you would have the same amount of matter as you would have antimatter created. Now, each of these pairs, if they meet each other, they'll collide, they'll annihilate and return to pure energy. So if you have a universe that's full of matter and antimatter, you'd expect that all these annihilations will have occurred and they'll have released energy. And so we would be left with a universe that is just energy. Obviously, that conflicts with observations. What we see is this kind of universe, which is all matter with the only occasional bit of antimatter out there. What has happened to give us a universe full of stuff? Our theory says it should have been antimatter and matter should have been created in equal quantities, but it's patently not true. Now, it could be. There are bits of the universe out there that are completely antimatter, big reservoirs of antimatter that have yet to meet other reservoirs of matter. Well, that doesn't quite tally because the universe looks the same in all directions. Maybe all these annihilations have happened, but there was an imbalance, an asymmetry in how the matter and antimatter was created in the first place. And again, that doesn't quite tally with what we understand. This, for example, could be tackled with the Large Hadron Collider, these high-energy collisions. They're going to be studying these new collisions to see if there's any inherent symmetry. Remember, those collisions mimic the early universe, high-energy collisions. Is there an asymmetry in terms of the amount of matter versus antimatter that's being created that could then illuminate why our whole universe is full of stuff rather than not stuff? And if you want to continue getting speculative, one very fashionable idea is that we are just one universe amongst many. That we just occupy one possible universe amongst an infinite set of parallel or alternate universes that all patchwork together to create something that goes by the name of the multiverse. It could be these are cyclic universes, or if you want to have multidimensional spaces, maybe you've got bubbles or pockets where you have continued most of the multidimensional space is carry on with the inflation, expanding away. Maybe you've got pockets where the inflation stops, and each of those bubbles, those pockets, turns into a universe. You can speculate away. Here you could have different laws of physics in different universes. You could have the same laws of physics, but you've got different initial conditions. You could have, as I say, this infinite multiverse patchwork. Sometimes the ideas arise out of an appeal of the anthropic principle, which is that we naturally inhabit the universe that is fine-tuned to support life like ours. But the problem with all of this multiverse stuff, for me anyway, it's interesting, it's fascinating, it is truly blue sky science. There is a point, though, you have to question whether it's true science. It is speculation, it is thought experiment. We are so far removed from producing any observable thing that could check these theories, could check these ideas. And it's quite unlikely to produce observable consequences in the near future. It may reap dividends for our physics decades or even centuries in the future, but I wouldn't describe this as one of the tangible problems that we can solve, certainly from the astronomical viewpoint. So let's move from the world of metaphysics, philosophy, this thought experiment, and to the things that we might be able to observe. And actually, that's quite limited as well. I've talked about how we're limited by whatever our available technology is, whether it's the detectors, the telescopes, the wavebands we can use. We're limited by the fact we can only directly observe 5% of the whole universe. Okay, it's quite a major constraint, because there's only 5% that is the baryonic, the ordinary matter that emits light or reacts to the light in any waveband. And then the other problem is that not all of that light actually can reach us. You've got to remember the universe is expanding, and the further away you get from us, the faster the universe is expanding away from us. Currently it's stretching by 0.007% every million years. That's how much distances change. And this is cumulative. That means there are some regions of the universe that are expanding away from us so fast, they're moving away faster than the speed of light, which is perfectly possible, by the way. The universe can do what it's like. Anything that moves, any light signals, any information that travels through space is limited by the speed of light, but the universe can expand away many times that speed if it wants to. But this is a problem. If you have a region of the universe, and maybe you go out far enough away till that region of the universe is expanding at the speed of light, you've got a galaxy there, that far away from us. Any light that leaves that galaxy can only travel at the speed of light. It can't outrun the expansion of the universe, and it will never get to us. And so we have an observable horizon. There's only so much of the universe that is within our grasp, where the light leaving any objects in that universe will ever make its way towards us. And as the expansion of the universe gets faster, this observable horizon is shrinking. Now, this isn't an immediate concern. If we're still observing billions of years in the future, we might begin to see galaxies wink out one by one, but that's not our immediate concern. It will shrink closer and closer to us. But at the minute, we can still observe enough of the universe, but be aware there's plenty of unobservable universe beyond that observable horizon. So this limitation of only being able to interact with the greater universe through light is something that might change. And again, this is the exciting promise that maybe, probably not in the next decade, but within the next few decades, we may have other kinds of astronomy, other kinds of ways of sampling the universe out there. So, for example, electromagnetic radiation, light, is produced by moving charged particles. Now, I'm going to talk about gravitational waves, and this is where you have a mass in motion, and it arises out of there's a wave solution to Einstein's field equations of general relativity. Don't worry about that, just take it as read. But one of the predictions from general relativity is that as masses move, well, you've got a stationary mass, you plonk it in the middle of space, space curves around it. The greater the mass, the more distorted space is around it. Now imagine that mass moves, then that distortion has to change. And gravitational waves are the ripples within the space-time that move out, sending the message of the change of curvature of space. And they move out at the speed of light from any mass in motion. Now, that mass has to be accelerating, so it could be spinning, it could be tumbling, and that motion can't be cylindrically or spherically symmetric. It has to be slightly asymmetric. But within that, there are plenty of chances where you can create strong gravitational waves. So, for example, imagine a dumbbell shape, a bone shape. If that's spinning around its axis of symmetry, it's not going to create gravitational waves. But if it tumbles end over end, it's no longer an axisymmetric, a perfect symmetrically situation, is going to create gravitational waves because it's going to rattle up the space-time around it. The more mass there is, the faster it moves, the more gravitational waves are going to move out and ripple out through space-time away from it. So examples of this could be where you have neutron stars or black holes in orbit around it. It could be asymmetric expansion of a supernova when it goes bang at the end of a massive star's life. It could be the merger of two black holes, or it could be an asymmetric black hole in rotation. These really energetic events have the potential to create gravitational wave astronomy. Now, we know gravitational waves exist. There's an observation from Hulse and Taylor in 1974 where they had two neutron stars in rotation around each other, one of which was giving off those pulse signals that made it a pulsar. The rate of energy, affecting this pulse signal was slowing down, showing that these neutron stars were losing energy. Every time they gave off a gravitational wave, there's an incremental loss of energy, which affects their in-spiraling, slows them down. And the amount of energy that was being given off from this matches exactly what you'd expect from gravitational waves. So we expect gravitational waves to be out there. The trouble is actually detecting them. They're very, very small ripples in the curvature of space-time. We only have a hope of detecting the most violent, the most explosive event, like a merger of two supermassive black holes when two galaxies collide somewhere in the sky, or maybe two neutron stars merging somewhere within our galaxy. And those kind of really explosive or highly energetic events are also the most rare. And so the prospects, again, this is really forward-thinking astronomy. The great thing about gravitational waves is that they will pass through solid objects, and it gives us the chance to penetrate regions that are inaccessible to light. So how do you detect a gravitational wave? How do you detect a change in space around you? And there's a characteristic signature that in any one direction, the gravitational wave is going to compress and stretch space and everything within it in a regular manner. And in one direction, that stretch and compression is going to be carrying on in one rate, and in a direction perpendicular, it's going to be out of phase. So imagine you have an experiment where you can measure distances on this, minute changes in distance between two arms of an experiment, and you look in one direction, then perpendicular to that direction. You're looking for this rhythmic change that is that's out of phase completely in the two different directions, that show you a gravitational has gone past and just squeezed space-time as it went through. The level of detection is minute. It's very difficult to do. We've been looking for gravitational waves for over 5 decades and have yet to really put our hand on our hearts and say we've detected some. But again, there are new and more advanced experiments coming online that hold the potential for this new kind of astronomy. So, for example, this is a video from the LIGO experiment. There's going to be a new improved advanced LIGO experiment that starts up later this year. Further along the line, we've got an experiment called ELISA. This is due, we're talking 2030 at best for the launch of this experiment. Later this year, there's going to be a kind of test mission called LISA Pathfinder that's going to be launched by the European Space Agency, which will just test one small component within this satellite. The ultimate idea is that you have 3 satellites, each a million kilometres away from each other, floating through space and making those precision distance measurements between the 3 satellites, again looking for those tiny, tiny variations that might happen to go past if there happens to be some major chaotic event going on somewhere in our galaxy or elsewhere in the universe. So this is very, very technologically challenging, but it has the potential to give us a completely new window on the universe. This would give us a new astronomy. And there isn't just gravitational wave astronomy. There's another form of astronomy which, again, is on the verge of opening up. And again, it may be a decade or a couple of decades before we can use it. But there isn't just light everywhere in the universe. There are neutrinos. Neutrinos, those neutral little particles that just flood the universe. You know, there's of the level of about 100 every cubic centimetre. These are emitted through nuclear reactions. So you're looking at maybe nuclear fusion. You're looking at radioactive decay. If you could see the sky in terms of the neutrinos streaming towards us from different sources, you would be sampling something completely different. The light that we detect comes from the surface of objects. The neutrinos emitted from the heart of objects, from the heart of stars, from the core, say, of a supernova collapse. This would give us, again, a completely different view of the processes and the physics going on out there that is not reliant on light. Trouble with neutrinos is we can see into the heart of things because they flood through matter. They don't interact with matter. We can only detect, one neutrino in millions that stream past us when they interact with some ordinary matter and produce like a flash of light. Here's another bond layer down in the Antarctic. This is an ice cube experiment that's looking to detect some of these ultra high energy neutrinos, which would come from the most exciting objects out there in the universe. So far, we've discovered neutrinos from the sun. We detected neutrinos when supernova 1987A went off. And probably we've amassed 20 to 30 high-energy neutrinos so far that come from somewhere outside our galaxy. We're not detecting huge numbers yet, enough to do neutrino astronomy. But the great thing about neutrinos is because they don't carry an electric charge, they're not deflected by the magnetic fields of the galaxy on their way to us. When we do start detecting them, we'll be able to know where they're being emitted from. We'll be able to look at the sky within neutrinos and again get a completely different view of the cosmos out there. So going back to the astronomies that we have, again, there are huge challenges. It's not just all these cosmological ideas of the multiverse, even quite basic things. We may not be able to detect the first stars or the first galaxies yet. That's going to have to wait, as I say, till at least the James Webb Space Telescope is launched, hopefully in 2018. Even the very distant versions of galaxies we see in the early universe, we've got to work out how they grow and they develop into today's galaxies. And a large part of this, as I have alluded to in the past, is the fact that they all seem to have a supermassive black hole at their core. Now, there are huge problems in this. You can grow a big supermassive black hole by accreting matter from stars, from galaxy collisions. We understand how you can grow these objects, but we see them when the universe was really young. How do you grow that much mass in time? Which comes first, the black hole or the galaxy around it? There is a key relationship between the two, that if you look at any massive galaxy, the size or the mass of the black hole at its core is related to the mass of that galaxy. Here's just a plot of the mass of the host galaxy over the mass of the black hole at the core. And you find that even the black hole at the centre could be 10,000 solar masses, it could be 10 billion times the mass of our sun. But it always tracks the mass of the galaxy. It's always about 0.3% of the mass of the galaxy around it. This suggests that galaxies and the black holes at their core grow in tandem, that one knows about the other, one affects the other. And we're still struggling to work out this feedback mechanism. Again, artist's impression. If we could get pictures this good, it would be easy. But again, looking at the processes around the black hole, looking at fueling mechanisms, looking at how the energy from the black hole affects the galaxy around us, helps us see how black holes might regulate galaxy growth and also the galaxy and the matter around it and how hot it is might regulate the growth of the black hole. But this is, again, is one of the more tangible problems that astronomers are working on right now. And it's not just the symbiosis of the black hole and the galaxy. A key thing is star formation, because this is what controls the structure and the chemical evolution of galaxies. It's the mechanism that drives the formation of galaxies, and of course not just within the galaxies, but also planetary systems around that. And that is hidden from our view. Where stars are formed are really inaccessible places. They're enshrouded by dust and gas, say within these wonderful pillars here. Within these pillars, you've got dark cocoons which are collapsing down under gravity to form new stars. And we cannot observe that star formation process directly. Now we're beginning to change that with new facilities coming online, probing millimetre and sub-millimetre wavelengths at greater detail. The most exciting of the new technological developments is ALMA. This is an array of telescopes which is picking up signals within this millimetre, sub-millimetre band that enable us to see right at the heart of star formation, see through these dust clouds, and in sufficient detail that we hope we'll be able to see actually material coming together under gravity. We're looking at the Doppler shift in that material, the kinematics of the signature that gives us the process of gravitational collapse. Instead of it all being hidden, we can actually see through to it. And you need to do it at these wave bands. You need to be able to see the protostar at the centre of the cocoon and yet also see through the gas and dust that's surrounding it. So not only is the hope that we'll be able to see the process of gravitational collapse, how fast it happens, how it happens for different masses of eventual stars that emerge from it, we can also see more about the raw ingredients that go into the star formation. What is interstellar space made of? What are in these clouds of dust and gas? We know they're molecular. ALMA's beginning to reveal the complexity of some of these molecules within the gas clouds. And not just within the gas clouds, but that has actually been incorporated into these cocoons in which the stars form. One of the most recent developments that has been quite exciting is looking, after the star has formed, the remaining cocoon that goes on and develops the planetary system around it. Now, this is an artist's impression, but just to remind you, you have the young star that's heated up, is beginning to shine. It's surrounded by a cocoon of matter. And within that, dust particles start sticking together. They build up to pebbles, gradually stick together under gravity to produce small protoplanets that then collide and smash. But generally, you grow planets within a disk of debris. With ALMA, you can now probe this entire process in a way that you can't see with any other waveband. Here, for example, is the young star HL Tau. You can't see what's going on. It's completely covered in the optical waveband here by gas clouds. Now, if you look right in the core of this gas cloud with ALMA, and this is not an artist's impression, you have the protostar at the centre there, and this is the disk of material that's forming planets around it. You have stuff that has begun to accrete to form protoplanets. And those protoplanets are beginning to clear stuff. So you have these gaps within the disk where there's a big planet that's actually gravitational clearing and tossing stuff out. We're beginning to get data of planets forming within disks that we can compare directly to computer simulations which predict these kind of structures. And again, here we're discovering surprises. They were looking at this protoplanetary disk. This star is only about 1 million years old. They were not expecting to find such massive planets, planets massive enough to have cleared distinct rings within the dusty disk already around the star. This means that planetary formation happens on a much faster timescale than we had realised. So again, there are still surprises. It can also, as I say, look for molecules within these disks. So here is a disk seen edge on around the star Beta Pic. Now, this is a slightly more evolved system. You've got young stars, you've got the star and you've got planets here. That's about the size of our solar system already formed. And then these are still building up, still crashing into each other. It's still quite an early stage of planetary formation, and the debris gets blown out to form the wider disk. And yet within this disk, you find concentrations of volatile compounds. And here you've got a burst of carbon monoxide and other molecules signature within the disk suggests that you've just had a major collision where you basically pulverize something the size of Mars. Because these volatile compounds, these molecules, are very fragile. They shouldn't exist for long. They've got to replenish them recently, suggesting we can actually start to trace when collisions between protoplanets, major collisions between protoplanets, have happened within these disks. So we're beginning to see processes of planetary formation, which I think is going to be revolutionary for the next few years to actually tap down what is happening to create planetary systems. And of course, this is where we've seen a huge paradigm shift. I talked about exoplanets 2 years ago. If I just showed you how the field has changed just in those 2 years, this is just the number of exoplanets discovered as an effect of time. Right, just for the last 2 years. Here, exoplanet research is changing hugely. We now know of at least 19,000 planets in about 1,200 systems, and there are plenty more candidates out there to discover. And the most fundamental thing we're discovering is that our solar system is not like other solar systems. These are confirmed exoplanets, their sizes. The most common kind of exoplanet is one type that we don't have in our solar system. In our solar system, you've got the rocky planets, big jump gas giants. The most common type of exoplanet around other stars is one where it's either a super Earth or a mini Neptune, something that sits within this region, about 1 to 4 times the size of the Earth. So the divide between a rocky planet and a gas giant is far less well determined than it seems in our solar system. We don't know, these mini Neptune super Earths, we don't really know whether they're rocky or whether they're gas giants. Maybe the mini Neptunes are ordinary Neptunes that have been bowled away because they're too close to their sun. There's lots of speculation, but again, it means that we're actually looking at what goes into a planet in greater detail and trying to work out the different characteristics of planets and changing our views about what kind of planets are out there. Super Earths, this is just an artist's impression of various super Earths that have been detected in comparison to the size of Earth. Again, they may not be dissimilar to Earth, and we can detect these, but actually finding anything like Earth is beyond our current technology. You can only detect something that's relatively close into its stars so that you detect signals of the planet moving in front of the star on a regular basis, so on fairly short time scales. We are not yet susceptible to finding Earth-like planets that are sufficiently far out to resemble our own Earth. We tend to look at dimmer, smaller, redder stars where they're much cooler, and you detect Earth-like planets that are about the same temperature as our Earth. They happen to be closer into their stars, so you see the occurrences of them moving in front of the disk more often. But it's not just the kind of planets we're detecting. We can, of course, characterize their atmospheres. If you have a very massive star that moves in front of it, so I'm talking a gas giant, a kind of hot Jupiter that moves in front of its sun, the sunlight gets filtered through its atmosphere during the transit here, and it imprints on it chemical signatures. So over the last few years, we've been able to determine what molecules are in the atmospheres of some of these gas giants. Developments are now that it's not just seeing this chemical imprint. If you don't see a chemical imprint, you can make inferences about the cloud layers within that atmosphere. We're beginning to detect which of these gas giants have what kind of cloud layers, or these super Neptunes have cloud layers on them. We're beginning to tell some things, not just about the chemical composition of the atmosphere, but also the climate within these atmospheres. Here, for example, is WASP 43b. This is something about the size of Jupiter, but it's got double the mass. It goes round its sun every 19 hours. Observations now can reveal the temperature profile across the atmosphere and within the atmosphere, meaning we can work out what the circulation is of air and heat from the day to the nighttime side of the planet. We're beginning to find out more about conditions on planets, but we're still limited to only really looking at the really big planets. This is the smallest planet for which we have detected the molecules within the atmosphere. This is about the size of Neptune. We've detected water vapor, hydrogen, and other molecules in its atmosphere, which is fairly cloud-free. Perhaps with James Webb Space Telescope, we can do similar science looking at the atmospheres of super-Earths. Even though we know there are Earth-like planets out there, finding stuff about their atmospheres is going to wait even longer than that. So again, you're looking long time frame developments in exoplanet research. But again, fantastic potential. Without having to go there, we can probe these other planets. So there are plenty of Earth-like planets out there. I mean, just statistically, extrapolating from what we know in terms of exoplanet candidates, we reckon that about 1 in 5 sun-like stars probably has an Earth-like planet around it within the habitable zone of its star. And just in terms of the whole galaxy, that means there are over 8 million possible Earth-like planets within the habitable zones of their stars. Here's just one example, around a sort of much smaller, cooler, dimmer star. It's about the same size as Earth. If this is where the Earth is in our solar system, it's much closer in, but it's within the habitable zone of its star. But again, actually detecting the molecules in its air, seeing whether it's got oceans, is so far several decades off, unless somebody comes up with a very clever way of using the data we have already to find that out. Now, just because it's in the habitable zone of a star doesn't mean that it's really Earth-like. There are all kinds of things about whether it's going to have the volatile compounds necessary to produce an atmosphere. And of course, the biggie is, does it have oceans? We think the oceans on Earth were delivered from a period of massive bombardment that happened 3.9 billion years ago, when the debris from that early stage planetary formation I was talking about crashes into the Earth. You've got comet-like bodies bombard the young planet, deliver the water and some of those volatiles. And it's a fragile balance. According to whether you've got material from the edge of the solar system, you've got these icy bodies, and whether they reach the inner planets. We think in our own solar system, Jupiter was essential in pulling material in so it crashed onto the Earth. But imagine you've got something that's more efficient at bringing stuff from the outer parts of the solar system. You've got so much bombardment, maybe life and oceans would never get going, because there'd be too much bombardment. Without a giant planet, maybe you don't have this bombardment and you just have a much more casual rain, and so oceans never get going. Looking at other solar systems shows us that this balance is not easily determined. And of course, with the idea that perhaps some of these gas giants maybe migrate in towards their sun, how does that affect the bombardment? And understanding that around other solar systems, it also means that we question how unusual it is for Earth. And there are questions still about where we get the water from Earth. Recent results from the Rosetta mission, sampling the water balance around this comet 67P, find like that the other comets that we've done so, it's got the wrong sort of water. It's enriched in heavy waters. This is water made with hydrogen with an extra neutron. It's got an additional neutron in its nucleus. It's slightly heavier. And it's got about 3 times as much heavy water than it should have. So either we've got to revisit ideas of where our water came from. Either the comets we sample nowadays are not representative of the ones that crashed onto the Earth a long time ago, or maybe we have to look at things like asteroids, icy objects, say like perhaps Ceres, that potentially those were the things that delivered water in this early bombardment. And so even when it comes so close to home, I still find it quite sobering and exciting to realise how little we know and how much we have still to learn about our own home planet. So it feels like there's never been a more exciting time in astronomy and cosmology. We've got new data, new ideas streaming in. We have the potential over the next few decades to find some of the very biggest answers to some of the most fundamental questions. And it really feels like we have so much left to learn. And I'd just like to end with a quote from, this is the very final paragraph from Hubble's famous book, Realm of the Nebulae, where he says, comments in 1936, which I think still hold quite true today. The explorations of space end on a note of uncertainty, and necessarily so. We are, by definition, in the very centre of the observable region. We know our immediate neighbourhood rather intimately. With increasing distance, our knowledge fades rapidly. Eventually, we reach the dim boundary, the utmost limits of our telescopes. There we measure shadows, and we search amongst ghostly errors of measurement of landmarks that are scarcely more substantial. The search will continue. Not until the empirical resources are exhausted need we pass on to the dreamy realms of speculation. Thank you very much.